We deal with data every day. Data has become the key ingredient when running a successful business. Data now arrives over every channel. We get emails, phone calls, messages, chats. We're bombarded by social media, and we get it 24 hours a day, 7 days a week, 365 days a year. Online retail customers now expect deliveries within 24 hours of placing an order. They want flawless engagements with ordering and supply processes while still demanding that personalised service. Thanks to the evolution of the internet, customers compare products, services and prices across numerous systems before buying. Meanwhile, artificial intelligence now helps us find the products we need, even when we didn't know we needed them. Psychological models and complex search algorithms drive us towards specific products, with analytics tools monitoring our every mouse click, gesture or purchase. A business has to react in near real time if it wants to keep its customer base. A modern business has to gain insight and predict as far as possible what the future holds. In order to support this, we need the right information presented in the right way at the right time. And underpinning all of this is data. At Capventis, we consider data to fall broadly into one of two categories: experience data or operational data. Experience data helps drive what you might think or do, and we can ask questions. How do you rate our service? Would you recommend us? And so on. In a simple shopping model, we might need to ask only a few questions, but these can identify real problems throughout the entire manufacturing and supply chain. Applied properly, survey platforms and analytics tools can help identify problems, reduce customer churn, and increase brand satisfaction. Operational data, by contrast, deals with processes and systems. Operational data provides the lifeblood of the business, helping to connect things, specify activities, and manage processes. With the right amount and type of operational data, businesses can predict what they need and when they'll need it. Way back in the 1st century, Hero of Alexandria invented the Steam Turbine. This, however, was only seen as a novelty, and few could think of any practical applications for such a device. It was an after-dinner novelty, a plaything. And there it languished for nearly 1600 years, until in 1698, Thomas Savory created a steam pump originally based on Hero's design. He needed something to extract water from his coal mines, which constantly flooded. Unfortunately, Savory's design lacked several fundamental components, and this made it inefficient and expensive to run. Some 80 years passed before James Watt, the noted Scottish inventor, mechanical engineer and chemist, added a condenser to steam engine designs. This addition transformed steam technology and springboarded the entire industrial revolution. James Watt, therefore, is the first of the curve jumpers I'd like to mention today. While there were many other steam designs starting to emerge at the time, none could offer the reliability, efficiency and performance that Watt's engine could provide. I could mention a few more innovators and curve jumpers throughout the Industrial Revolution, the discovery of electricity, radio and wireless communications, or on to the development of integrated circuits. But instead, I'll focus on a few of the more recent innovators. Throughout the 1950s and 60s, computer technology started to mature. Storage was becoming cheaper, and with the evolution of the hard disk, databases became more common. And after departing Ampex, Larry Ellison, Ed Oates, and Bob Miner launched their first product. That product, a relational database manager, was finally rebranded as Oracle in 1995. It is, of course, the largest database company in the world today. On the 12th of August in 1981, IBM launched the personal computer. Now, the IBM PC wasn't necessarily the fastest or best computer at the time. Certainly from a technical perspective it wasn't. However, IBM held a dominant position in the computer industry at the time, and it created a competitively priced machine that sold way better than any of the analysts thought possible. However, I don't consider IBM a curve jumper. Instead, I think that trophy goes to Compaq. Compaq took the IBM BIOS, the computer's firmware, and reversed engineered an entire hardware platform from its API so that its machines could comply with the IBM BIOS specification. In effect, Compaq demonstrated that any hardware manufacturer could make a computer capable of running any IBM PC compatible software. This created a whole industry of IBM compatible machines, and some of that original design ethos became so standardized that it still persists to this day. Curve jumpers take more than just an evolutionary step. While the rest of the industry gradually improves or introduces point changes, curve jumpers take an entire market sector in a new direction. On the 9th of January 2007, Steve Jobs did exactly that with the introduction of the iPhone. Here, he presented a handheld device that combined many other technologies available at the time. For the first time, a consumer could have a touchscreen phone complete with internet browser, music player, map viewer, and even a YouTube client. Overnight, this device displaced other dominant technologies from the likes of Nokia, Microsoft, and BlackBerry. Dgraph earns its place on the curve jumpers list because of the way it handles data. In a conventional SQL database, we have to represent data in a list of fields, each identically structured. Let's take an invoice as an example. Here we need a unique reference and a date of issue. Talking of issue, we need to have someone to receive it. So here's a person, and the person needs to work or live somewhere, so let's add an address store too. An invoice has one or more line items, giving the quantity and price of products. Then we have the product information itself, in this case another reference and description. So here we have our basic entities. However, in any database model, we need to define how these various entities link together. Here in the SQL world, this comes at a cost. We need to add additional intermediate lookup tables. These intermediate tables should only represent methods to cross-reference things. Person to address, person to invoice, invoice to line items, and line items to products. However, in reality, these often end up defining the business logic for the entire application. And this gives rise to a few problems. Anyone looking at the tables alone has no way to understand the relationships between each of the entities. How do I know, for example, whether the person's address represents the home or billing address? I lose sight of how these entities relate to each other, and, more often than not, queries end up holding intermediate values or managing context rules, meaning that I have to search through database queries to find out what my system is really doing. And the queries themselves become ever more complex. At some point, I have to understand whether I need an inner join or an outer join, whether inner selections will invalidate other parts of the query, and I have to understand the table schema from a design perspective before I can expand my system. In many cases, we come across horrific SQL, put in place by some database administrator with a personal vendetta against anyone daring to use their database. And yes, this is a single query. And yes, it's real. That's enough pain. Let's talk graph again. We still have the same entities to consider: person, invoice, address, line items, and products. But when I come to linking these, I can define the context in the link itself. I'll go ahead and add a billing edge to a person. And that would point to an address node. Note that I called this billing because I might also want to point to a home address, and I can do that by adding a home edge and calling it home. By looking at person, I know instantly that I have their first and last names along with their billing and home addresses. At this point, I don't care if I don't have all the information. The business logic will define the rules. So if a person must always have a billing address for the invoice to run, that's up to the business invoice logic, not the database. Now I'll add a link to the invoices themselves. In this case, the square brackets define 0 or more invoices. The database is telling me the context of the link and how it expects to see them. We can do the same things with items and products, and if I want to get flashy, I can start adding facets to each of the edges to carry additional information about the link itself. Generally, I try to avoid this. I prefer to do this kind of thing via edges in and of themselves. Now we start hitting the curve. Dgraph lets me query directly against the database using GraphQL. And this means a single query like this can do the invoice run. And the data I ask for comes back in the result. Where I start getting excited is the ability to use RDF. And actually, this shows a major curve. Dgraph's concurrency. I'm vastly simplifying things here, but in principle, I'm starting at an invoice record. It has edges pointing to other nodes. Dgraph shards on these, meaning that each edge can sit on its own server if it wanted. Each of the requests runs in parallel. This means I get a huge performance gain from using Dgraph. This is the main advantage of using a native graph database that doesn't rely on fixed structures. As I introduce new edges, Dgraph will sort out how best to shard and handle it accordingly. Continuing along the curve, Dgraph also lets me do things via single queries that would be difficult to model otherwise. This, for example, shows a real-world data cleansing case. When we ingested the data, we found an entire section of the business was disconnected from everything else. Another view showed that these entities also had different management teams. Again, not connected to the rest of the business. After we worked out where these tasks should go, we ended up with an integrated model where all the processes and associated business activities joined up, and we removed a lot of duplication or redundancy in the process. Dgraph has taken us into an entirely new direction. We don't worry about scalability, and we have blinding performance compared to other graph and database systems. We use GraphQL and, via Dgo, use a DQL client a lot too. Because Dgraph also provides native RDF support, we also employ that when doing a lot of edge grouping or linking activities. This improves our development throughput, reduces maintenance costs, and helps us grow organically. In the day job, I look after a very technical landscape. We deal with customer engagement through support systems and ticketing platforms. This crosses over into experience management, where we can measure employee and customer experiences and collect key performance metrics. Now I have the data, I'd like to gain insight from it so that I can improve quality and performance, or reduce costs, or meet other business needs. For that, we have a data science team, and working in conjunction with our analytics teams, we help companies derive value from the data. After all, there's little point in collecting it if you're not going to use it. While we use other tools and systems, I'm showing our preferred partners here. Zendesk for best-in-class ticketing, Qualtrics to help measure customer or employee experiences, Qlik for data visualization, and of course Dgraph for its three products, Ristoretto, Badger, and Dgraph itself. With all of these tools, and with others in these market sectors, we need a way to integrate, synchronize, and manage data. And for that, we have our own internal system, affectionately known as Glue. Glue works in harmony with Dgraph, Badger, and other data sources to handle complex integrations with ease. It provides a scripting engine based on Google's Go programming language to federate GraphQL endpoints. It acts as a GraphQL wrapper around legacy interfaces such as SOAP or message queues, REST or custom APIs, database links, and so on. Glue has a central core and can work on bare metal or at higher levels through the stack as required. Its core engine has shifted between two different scripting environments. For the original model, we used a TypeScript engine, but battled with making it support concurrency and things that the Go language supports natively, channels, mutexes, and so on. As a result, we built a Go-based scripting engine, allowing us to concentrate on functionality rather than getting buried in language semantics. Lifting the covers off the core reveals a whole host of process management services, and these coordinate and synchronize between services, scripts, and provide state machines for the scripts themselves where necessary. Each runs in isolation to protect process integrity and maintain security. The engine wraps calls via a virtual import mechanism, and this provides direct access to Dgraph Badger or its own internal mapped data and processing services. As a result, there's minimal overhead when calling Dgraph native functions from within scripts or when making requests to Dgraph Cloud. With Glue's high-performance parallel integration and Dgraph's horizontal scalability, we have a laser-precise and lightweight integration service that can handle almost any volume of data in real time. We leverage Dgraph's Jepsen-tested transactional integrity within Glue to give extremely robust data management and synchronization across disconnected or asynchronous processes. So let's put this into the real world. With Glue, we can, for example, track events in Zendesk so that when a customer opens a support ticket, we validate within 0 that the customer has an account with us. And for those on a drawdown support contract, that they have sufficient credit to allow us to resolve the ticket. If not, we send a message via Pipedrive to our sales team. Assuming that this customer has sufficient credit, we can allocate team members to deal with the support issue, having passed the ticket through Google Translate and Amazon's Comprehend to analyze sentiment. Then we send it over to Reich to manage the projects themselves and log the time spent. Finally, raising invoices back in 0 against the support project for the client. When it's all over, we bring in Qualtrics. Now we can measure the performance of our team. Was the matter resolved satisfactorily, and how was the service overall? How can we improve things in the future, and so on. This feeds back into the organization to help the business get better at what it does. Glue handles the interfaces. Dgraph keeps track of all the various systems, key fields, custom entities, and so on. Once again, back through Glue, we pass this to Click or Power BI or Tableau to provide dashboards and to help predict future support requirements. We're currently extending this part to provide a wrapper around BI tools to allow them to work directly off of Dgraph. You might have noticed that everything within that landscape sits within its own system. Zendesk handles the tickets, Xero the accounts. Pipedrive handles sales data, and so on. We don't need to move all of this data. Instead, we link to it, and we use Dgraph to help us maintain consistency and referential integrity throughout. The Jepsen tests become really important in this context. When I search for information via Dgraph, I know I'm getting a single, consistent view across all the platforms. Within Capventis, we run Dgraph in several contexts. For developers, the flexibility allows us to iterate through schema changes without impacting other services. When running integration or migration programs, we use Dgraph to help us analyze the structure and composition of our data. And for our BI teams, we can choose where best to run analytics functions. Do we aggregate and simplify data within Dgraph queries, or is it better to pass raw data directly to the likes of Tableau or Click? And this brings us back to curve jumping. When I first came across Dgraph, I like things like the horizontal scaling and the ability to use things like RDF for data updates. I like DQL, the Dgraph extended query language, to search for data. However, Dgraph hasn't rested on its laurels. Instead, the team continues to develop and provides us with a way to go from initial proof of concept right through to commercial models simply by changing the connection URI. With the advent of Dgraph Cloud, we find ourselves in a position where we can offer implementations in several ways. For development and early test, and for smaller projects, we use open source instances within Docker containers. For the medium-scale production environments, we can host in AWS or Azure. When things get a bit more serious, we need enterprise-grade features. And for this, we can switch to our own hosting or use Dgraph Cloud. All of this is a seamless transfer. We can add nodes if we're hosting, or we can just pass the management of the whole thing and its associated infrastructure over to Dgraph Cloud. Not only that, Manish and the team brought GraphQL to the front of the stack here too. We still drive a lot through the Dgo interfaces and use both RDF and DQL across them. However, we also have the option to bring in native GraphQL services within the Glue federation layer. With the GraphQL model, I can upload a schema, and Dgraph does the knitting behind the scenes. It provides all the standard functions required to integrate and update the data, and it does it instantly. It's extremely quick. And for schema-driven organizations or developers, it's a hugely effective way of managing data. When I first started our Glue project, I wanted to create something that I could use for discovery, integration, and orchestration, and do all of this at scale. We adopted Dgraph early on because I needed to find a flexible way to link data and let the integration services evolve naturally. This gave me a constantly changing landscape where I may need many integration microservices all linked together. Glue therefore deals with the APIs and message queues. It can federate queries across multiple backends, and it can operate as a single instance or part of an integration network linking multiple Glue instances together. I can run multiple Glue engines, each supporting concurrent and parallel scripts. Each of these scripts potentially handling concurrent transactions. It crosses the boundaries with components working inside the customer's infrastructure, or in the cloud, or across private and containerized networks. Conventional databases would force me to work in a different way. Dgraph frees me from the constraints imposed by traditional tables, with all that key field management and complex SQL, which invariably hides business logic in a hidden database layer. All of that's gone. Beyond Glue, Capventis has started building a platform. We've based it entirely around Dgraph. And while it's early days, we're already seeing the benefits of building websites from the ground up, using a flexible schema and having GraphQL as the primary API, with resolvers handling distributed queries and mutations, and any front ends simply plug into this entire model. Dgraph lets me work with data. It removes many time-consuming and restrictive processes, and it improves data visibility. In my integrators world, I can see anomalies before they become a problem. We live in a technical world. We now have better ways of handling data, and Dgraph helps us to do that. For those reasons, for me, Dgraph jumps the curve. It scales, it performs, and it lets me keep data in place, or I can bring it inside the database. It has transformed the way we work. Instead of trying to shoehorn business processes into a restrictive model defined by legacy database systems, I now concentrate on the business needs and let the data support those needs. Here at Capventis, we're looking forward to a bright future, and we're extending our Dgraph team. We're hiring. We're developing new platforms for our clients with Dgraph. It's become a fundamental component in our development, and long may that continue.